One thing that is stipulated in our section on the atomic theory is the idea of Rutherford's experiment. And now this is going to be a short review of it, and we're talking about his gold foil experiment to actually give us a better insight about what actually is inside the atom and how things are arranged. And in some ways it was quite a bit of an eye-opener. It was a very innovative way of doing things, I think, but it all boiled down to the fact he was able to use the newly discovered idea of radioactivity and radiation to help him do this, and he tended to use a particle, as we'll see in a moment. Rutherford decided to use the alpha particle, and the alpha particle has mass, so in other words it wasn't going to simply just penetrate. If there was something there to bump into, it was going to bump into it. Now from the picture we see the alpha particle has 2 protons and 2 neutrons. So essentially it's a helium nucleus. And it's rather a large particle when you think about it. So he decided, yep, this looks like a good little bullet I can use to shoot at atoms. So what he did was he arranged an alpha particle source. In other words, this material only released alpha particles, and by closing it in a lead box and having only one area opened, he was able to direct a stream of alpha particles at his screen. The other interesting part about the alpha particles is that they all have a positive charge. So they will be, like all charges, they'll be attracted to negatives and repelled by positives. And this becomes important later when we actually look at what he found out. And he used this idea of repulsion and attraction of charges to help him understand more about what was going on inside the atom. The picture on the right of the screen actually shows us basically the mechanism of what he did. As I said before, he had the lead box so we could direct a stream of them in a particular direction. He used gold leaf in the middle of it, not because he wanted a very expensive experiment, but because gold is quite dense. In other words, the atoms are packed really, really closely together. So this meant he was firing a particle at targets very close together, very closely packed. And this he assumed certain things were going to happen. Now notice around the outside he has a screen. And the screen's not like a normal screen, it's more like a fluorescent screen. In other words, when a particle hit it, it would glow. So we'd get flashes to say where the particles were hitting the screen. He was able to see this. And that's really, really clever when you think about it. By the way, this is the basis for the old TV screens before plasma and our newer screens that have come out, new thinner screens. So he started firing these alpha particles at the screen, and lo and behold, he got quite a few of them just going straight through. Now that says something in itself. If you're firing something at atoms closely packed together, but you're missing them, then the alpha particles just keep going straight through. So this implied to him there must be something going on inside. Then he saw that a certain number were deflected a little bit away from their straight course, and as we see them on the bottom down here, we see them, these ones, the ones that were deflected a little bit away. Here are the ones that went straight through. Here are the ones that were deflected a little bit. Right, so that implies they must have come somewhere near a positive centre. But then he got these ones over here. These ones that came back, almost deflected back towards him. And they were very interesting themselves as well. So he had to work out what this all meant. So if we think a lot like Rutherford, and we think a lot like what's going on, then we can see it's got a couple of models here to say what was going on. So he was comparing them also with the Thomson and and another model, he suddenly worked out, whoa, hold on, if I'm firing them into Thomson's model, none of them should go through. I've got these negative charges embedded in a positive mass. So, whoops, it should all be deflected. I shouldn't get any going through. So if they were going straight through on the path through here, straight through, they must be missing any of the particles in here. Alright? So we said the ones that went straight through because they missed. So that meant because there were so many going straight through, there must be a hell of a lot of space for them to fit through. Which totally goes against the idea of what we think with really, really solid, closely packed atoms in things like gold. Alright? Then if it deflected a little bit, it meant that he suggested that it meant it came near to this positive centre, this positive nucleus in here. The particle got near it, and so we had electrostatic repulsion factors going on. So it would force it away from going straight through. It would be repelled as it came close. And then if you think about it, the ones that almost came back at him were the ones that almost were fired directly at this central nucleus. So if they went there, then it's going to be deflected back this way. Alright? So it's going to go in and then come back this way. So this was the evidence, and this was his conclusion, that as you push these alpha particles in, most of them went through because there was nothing there for them to hit. In other words, there was empty space in the atom. If it came close, but not too close to the positive nucleus, the alpha particle was deflected away from the straight through. But if it came almost at the nucleus, then the particle was deflected back towards the source. And that is how Mr. Rutherford came up with his theory of the atom, which has got a positive nucleus in the centre here, and the negatives outside in this empty space, moving around much like planets orbit the sun or the moon orbits the Earth.